magnetic field. Okay, so before discussing the Earth's magnetic field, we'll discuss about magnetic field lines. So now, in the previous classes, what we have discussed is a bar magnet and a solenoid behave similarly and gives us the same type of magnetic field. So it can be termed as both as north and south pole. So over here is a bar magnet which has got north and south pole, and this is a solenoid which has got north and south pole. Now the magnetic field lines, the pattern of the magnetic field lines are like this. So the magnetic field lines emerges from north pole and ends at south pole. It forms a loop. Okay, it doesn't end over here. Actually, it moves from south to north. It forms a kind of a loop. Even over here, it forms a kind of a loop. Now, properties, there are a few things we have to remember to find the direction of the magnetic field lines at every point. What we do is, if you want to find a magnetic direction of magnetic field lines at any point over this field, we draw a tangent at that point. So tangent means a line just touching the surface of that loop. So we draw a tangent at any point if you want to find the direction of the magnetic field, and direction will be from north to south. So now I have told you tangent, to find the direction we draw a tangent. Now there are few properties of magnetic field lines. Okay, you need to remember these properties. First one is magnetic field lines forms a closed loop, which is not as electric field lines. Electric field lines is not, it doesn't form a loop, it is a straight line. Whereas magnetic field lines, it forms a loop, it forms a circle. Okay, not exactly a circle, but it forms a loop. It has the starting and ending point will meet at one point. That is the first property, which is different from electric field lines. Second property is magnetic field lines never intersect one another. You can see this magnetic field lines will not intersect the other magnetic field lines. Even inside the solenoid or bar magnet, where the magnetic field lines are very close to each other, they will not touch each other. They are separated by a very small distance, and it will not cross. What happens if magnetic field lines crosses each other? If it crosses, then a tangent, to draw a tangent over there will not be possible, because the tangent will show two different directions, and magnetic field lines does not have two different directions. That is why it will not cross each other. The third point, fields are stronger near the poles. You can see that over here. In the poles, the magnetic field lines are very close to each other. So the magnetic field lines at the poles are strong. As we move away from the poles, the field strength will decrease. Okay, it will decrease at where the magnetic field lines are separated by its distance. Wherever the lines are compact, more the strength of the magnetic field lines. Fourth one is, inside this solenoid or inside the bar magnet, magnetic field lines are uniform and equidistant. Okay, parallel and equidistant, which means it is uniform. Fifth one is, no lines of force in the neutral point. There will be a neutral point. I'll tell you what is a neutral point. The point where there is no magnetic field lines is the neutral point. So over here in this image, okay, over here you can see this image, there are two magnets. This is north pole, south pole. So whenever a magnetic field line emerges from north pole, it ends at south pole. Okay, it ends at south pole. So over here in the center lies a neutral point where there is no magnetic field lines and there is no effect of magnetic field. The magnetic field strength cannot be felt over there at the center of two poles. So this point is a neutral point. Over here, when we bring the same pole together, the magnetic field lines will repel each other because it's south and south pole. It will not touch, it will repel. So over here at the center is the neutral point. So these are the few properties of magnetic field lines. Now let us move on to Earth's magnetic field. Okay, Earth's magnetic field. Now Earth itself, okay, you have to remember that. Okay, it will be a little confusing, but you need to remember from the beginning. Earth itself behaves like a magnet. It is a very powerful Earth has got two poles, North Pole and South Pole. We are not talking about the geographic pole. There is another pole known as geomagnetic pole. Okay. Now Earth behaves like a powerful magnet. South pole of the magnet point towards the North pole of Earth's magnetic field. Now, if you take a magnet in your hand, if you have a compass in your hand, the tip of the compass will point towards the North pole. So, actually, a compass is the tip of the compass is north, and the tail of the compass is south. So, the tip will point towards the North pole of the geographic Earth. So, over here, if you place a compass, the tip of the compass actually points towards the North pole of the Earth. But actually, North pole and North pole will repel each other. So, what I mean is, wherever the geographic North pole is there, that is the geomagnetic South pole of the Earth's magnet. Okay, and wherever there is the South pole of the geographical Earth, there lies the North pole of the Earth's magnet. Okay, Earth is a magnet. In the North pole, geographic North pole, there lies the South geomagnetic or the South Earth's magnet, South pole of the Earth magnet, and wherever is the South pole of the Earth, South geographic pole of the Earth, or what we call the Southern Hemisphere, there lies the North pole of the Earth's magnet. Okay, the Earth magnet. Earth is a magnet, so South pole of that magnet is actually at the north, North pole is actually at the south. So it will be a little confusing, but try to analyze this. If you place a compass, the North pole will point towards the North pole of the compass will point towards the South pole of the Earth's magnet, and the tail, where is the South pole of that compass, will point towards the North pole of the Earth's magnet. So now over here, there are a few things we need to remember. That is, how can we consider Earth as a magnet? What are the reasons behind considering Earth as a magnet? Suppose we take a compass, a freely suspended magnetic needle. Okay, if you can freely suspend a magnetic needle, it stays in a north-south direction. That means if you place a compass anywhere at the surface of the Earth, the north pole of the magnet will point towards the north direction, and south pole will point towards the south direction. That is the first reason that Earth can be considered as magnet. Something is pulling the compass towards north and south. Second thing is, iron piece buried in the Earth becomes a magnet. If you bury an iron inside the Earth surface, then if you take it out after many days, then what happens? That piece of iron behaves like a magnet. That is the second reason why Earth can be considered as a magnet. Third is neutral point. In the Earth also we have got a neutral point where there is no effect of magnetic field. So if there is no two magnets coming nearby, we don't get a neutral point, like in the previous case over here. If there is only two magnets, then we get a neutral point. So if you bring a magnet in the Earth's surface, there is a neutral point which exists. It means that one magnet which is there in your hands and other magnet is the Earth itself. So there are two magnets, and then we can see a neutral point. Now the strength of magnetic field of Earth is 10 to the power minus 4 Tesla. Remember this, the magnetic strength of the magnetic field is 10 to the power minus 4 Tesla. And magnet, when we bring a magnet and we take it to different places on the Earth, it behaves differently, because it is interacting with the Earth's magnetic field. So it proves that Earth is a magnet and it has a magnetic field of its own. Now Earth's magnet, you can see over here, this is Earth, okay, and it is a magnet. The south pole of the Earth magnet points towards the northern hemisphere, north pole of the Earth magnet points towards the south pole of the southern hemisphere. So it's actually the magnet is inverted. The Earth's magnet is inverted. Earth is a magnet which has an inverted pole. South pole is over here and north pole is over here. Now, This is the axis of rotation. Earth rotates in its axis of rotation. But this is south magnetic pole and the axis of rotation and the axis of the magnet is not at the same place. This is the axis of rotation. It rotates, Earth rotates like this. But the magnet is like this. That means these two lines are not at the same place. If this is Earth's rotation, then this is the magnet kept like this. So it is not at the same place. So magnetic field emerges from the magnet and the Earth rotates like this. So now these are the field lines and this is geographical. At this point lies the geographical south pole. This point is the geographical north pole, where lies the south magnetic pole of the Earth. Over here lies the north magnetic pole of the Earth. Now the magnetic field lines. We need to discuss about magnetic field lines, how it is at different places on the Earth. You can see that over here, the magnetic field lines, this is the equator, okay, here lies the equator of the Earth. So at the equator, the magnetic field line is parallel, okay, you can see these lines are parallel. It is parallel to the Earth surface. Remember this, parallel means theta will be 0 degree. That is horizontal, okay. Parallel, 0 degree, horizontal, it makes sense because this is Earth surface, it is parallel, angle is 0 degree and it is horizontal to the Earth surface. Suppose this is the Earth surface. Okay, if we have the Earth surface, my hand is the Earth surface, the magnetic field line is like this, on top of the Earth surface like this. But at the poles, what about the magnetic field lines at the poles? At the poles, the magnetic field line emerges from the upward direction. So this is the Earth surface. Earth surface at the poles will be flat. Then magnetic field line emerges like this. Okay, from north pole it emerges towards the south pole. So Earth surface magnetic field line, it is perpendicular. Theta is 90 degree. Similarly, over here at the north geomagnetic pole also, the magnetic field line emerges from the downside. So it will be, the Earth surface is like this. At the south pole, the magnetic field lines is coming from down. So it is again perpendicular. So magnetic field line at geomagnetic poles is over here, it is perpendicular. At the Earth surface or at the equator, it is parallel or horizontal. At poles, it is vertical. Now, the next thing is, over here I told you the axis of the this is the magnetic axis, this is the Earth axis. So this makes an angle over here. This angle is known as angle of deviation, which is denoted by alpha and which is measured around 11.5 degree. Okay, the difference of magnetic axis and Earth axis is 11.5 degree. But with time, this angle keeps on changing. It is not fixed. The magnet of the Earth magnetic field, it keeps on changing with the axis of rotation. It is not fixed. And if you consider the Earth's magnetic field at a small area, suppose inside this room, the Earth's magnetic field inside this room, if you consider a small area, it is uniform. Okay, it is uniform. It doesn't change from one corner to other corner. It is uniform. But if you consider the whole Earth, it is different. If you consider a small area, it is uniform. Okay, now let us discuss about components of Earth's magnetic field. Or this is another diagram to make you understand the Earth's magnetic field. I'll explain again. Okay. Now look here. This angle, this is Earth's magnet having south and north pole. I already told you Earth is a magnet whose south pole lies on the geographic north pole, whose north pole lies on the geographic south pole. Now from there emerges the magnetic field. The axis, the line which passes from north pole to south pole, this is known as magnetic meridian. Okay, it is also referred as magnetic meridian, or you can also refer as magnetic axis. This is the magnetic axis. This dotted line over here is the axis of rotation of the Earth, where the Earth rotates. Angle between these two is 11.5, which is denoted by alpha, which is also known as angle of declination. Now this dotted line is the equator. This dotted line is the magnetic equator. There are two equators. Dotted line passes from the center of the magnet. It is known as magnetic equator. Dotted line which passes through the center of the earth is the geographical equator. There are two equators, magnetic and geographical equator. Magnetic equator passes through the magnet of the earth, and the geographical equator passes through the axis of the equator which we study in geography, that is geographical equator. Now there are two poles. This pole over here is the geographical south pole, southern hemisphere. This pole over here is the north magnetic pole of the earth. Over here is the south magnetic pole of the earth. This is the geographical north. I hope this image is clear. Now the next topic will be elements of Earth's magnetic field. There are different elements of Earth's magnetic field. Now why are these known as elements of Earth's magnetic field? Because if we have the idea of how much this is, or if we can find the elements of Earth's magnetic field, then we will have an idea of the strength of Earth's magnetic field, and in any place of the Earth we can find the Earth's magnetic field. With the help of this, or in simpler words, with the help of this element we can find the Earth's magnetic field. Now, first one is angle of declination. I have already told you before, the angle between magnetic meridian and Earth's meridian, or the axis of rotation of the Earth and axis of magnet is the angle of declination. So this is the geographic meridian, north pole of the north pole, which we call the northern hemisphere, so the south pole, which is the southern hemisphere, and this line is the magnetic meridian. A line passing through the magnet, line passing through the center of the magnet. Over here lies the south pole of the Earth's magnet, over here lies the north pole of the Earth's magnet. Angle between these two lines is known as angle of declination, which was 11.5. I told you it keeps on changing with time. It is denoted by alpha. Remember that it is not written over here anywhere, but please to make a note, it is denoted by alpha. Second one is angle of dip. This will be quite confusing, but remember that this is a dip machine. Okay? To measure the angle, we have this kind of a device. To measure the angle at different points, we have this kind of a device. Now, I already told you the angle between the magnetic field and the Earth's surface. Suppose this is the Earth's surface flat at the equator, magnetic field lines. It is parallel. So what is the angle? 0 degree. This angle between the magnetic field and the Earth's surface is known as angle of dip. This keeps on changing. Okay, this keeps on changing. It is 0 right now. If you move on towards the pole, it will keep on changing. It will keep on increasing. And at the pole, what I have told you, magnetic field line is perpendicular to the Earth's surface. This is the Earth's surface, magnetic field line is perpendicular. So at that point, angle of dip is 90 degree. So what is angle of dip? It is the angle between magnetic field and the Earth's surface. That is the angle of dip. It is denoted by theta. Okay, it is denoted by theta. Please remember that because we need this in derivations and all. The last and third component of Earth's magnetic field is horizontal component of Earth's magnetic field. Now I have told you, magnetic field is perpendicular at the poles, parallel at the equator. But any other place in the Earth, it has got some angle. Okay, it has got some different angle. And we know that when there is a difference, when something is not perpendicular, something is not parallel, what we do is, magnetic field line is a vector quantity, we resolve that into two components. Okay, if it is not horizontal, not vertical, we resolve that into two components, one vertical, one horizontal. So that horizontal component of Earth's magnetic field is denoted by VH. Now, this image is an image of cross section of the Earth. Suppose this O over here is the equator, middle of the Earth. This point is the geographical north. This point is the magnetic north. Angle between geographical north and magnetic north is alpha, that is angle of declination. Okay? And the angle of magnetic field with the Earth's surface is theta, that is angle of dip. Now, over magnetic field at the Earth's surface. Now this we are resolving it into two components, that is horizontal and vertical component. BH is horizontal, VV is vertical. This angle over here is theta. Now over here we can easily find the value of BH. That is, whenever we want to find the horizontal component, we replace that with cos theta, or cos theta is equal to base divided by perpendicular. In the next slide, I have got a simple derivation, so you need to understand this. Okay, BH is the horizontal component. For horizontal component, we use cos theta. Done several times. I hope you know this. BV is a vertical component. This is represented by sin theta. Okay, BE sin theta and BE cos theta. Now to find the value of BE in the previous image. Okay, the BE is actually a horizontal. This BH, this side is base. This side is perpendicular. Okay, so this becomes a right angle triangle. So you can use a Pythagoras theorem to find the BE. Pythagoras theorem is BE square is equal to BH square plus BV square. So from here, what you can find is you can find theta, that is angle of dip. Now why this is important is, with the three components of the Earth's magnetic field, that is angle of declination, angle of dip and horizontal component of the Earth's magnetic field, if you know these three values, then we can easily find the magnetic field at any point in the Earth. The only difficult part is the angle of dip. Okay, in the previous image, the angle of dip, theta, angle of declination alpha, keeps on changing with time. It does not only change with the place in the Earth, because at every place on the Earth, these two angles are different, but this also changes with time. That means the magnetic field of the Earth, or the magnet of the Earth, this magnet, which is the Earth's magnet, keeps on changing. It is not fixed. It has been changed since like many years. It will keep on changing. So that is a difficult part. At different points, at different place of the Earth, the angle of dip is different, whereas with time this keeps on changing. So if we know the value of the angle of dip at an exact time, then we can easily calculate the Earth's magnetic field. So with this, we have come to an end to this chapter. Now in this chapter there is no IC numerical, so I will not doing any numerical. I will not doing any numerical. In the next class, I will start a new chapter. I hope till here it is clear and helpful for you people. Please do make a note of all these things. This much for today. Thank you.